Hi, we're involved with a problem of trying to optimize the number of add-ins of 25 that when multiplied will create the biggest product. And we're gonna tackle this with an optimization problem from calculus. Find the derivative of our expression, quantity, quotient 25 and n is raised to the power of n. That tells us our max area or max volume or max hypervolume or biggest product of equal sized values of add-ins of 25. But there's a problem here because this n is contained inside a quantity that has a power of n. So we need to do a little bit of working around. We're gonna go through properties of logarithms. So we still need ddx or ddn, habits, right? We still need ddn, but writing this as is a no-go. So we need to use the fact that the natural number e raised to the natural log of e is really just like they're equivalent to not writing them at all. So we're gonna go e to the ln of 25 over n. So this expression is still raised to the power of n. So I'm getting a little bit, handwriting sloppy with the notes. Hope you're okay. The fact that, this is here. Another property of logarithm says that if there is a power inside the logarithm, that we get to move that power out front. That is an equivalent relationship. So this really becomes ddn, can't lose that, we haven't done anything with it yet, times e to the power of n ln of 25 over n. So now we can use our understanding of derivatives to figure out what this is. Anything as e to the power of, whatever, will bring that back around. So we will still have e times n to the ln of 25 over n, but you have to also multiply by the derivative of this because of the chain rule. So the derivative says, I'm gonna use this f, or initial term, multiplied by this one, and there is a process that is a shortcut for product rule for derivatives that says that this is also an embedded chain rule, it's an extensive problem. The first product, the first factor, will find its derivative, which happens to be 1, multiplied by the second factor just as is. So 1 times the ln of 25 over n. And then we add to that the first factor, keep it as is, times the derivative of this. So we're gonna keep n, but then we're gonna multiply by the derivative of natural log of 25. That's not difficult, but it is gonna rely us to do some u substitution. So just a note on the side, dn of natural log of 25 over n is, well, the derivative of natural log is 1 over the argument. So 1 over 25 over n. Then we have to use the chain rule. So we have to multiply by the derivative of 25 over n, which is negative 25 over n squared. You see n has a power of -1. So then properties of products, or not properties of product, properties of powers would tell us that we're gonna make this 1 power as a denominator become a 2 process. Okay. Lots of stuff happens. Some simplification happens here where this 25 over n actually can be rewritten as, n over 25, forgive me, because this is a fraction in the denominator and we want to use reciprocals to flip it. This is going to flip over, so you have n over 25. These 25s will cancel. This n and one of these n's will cancel. So actually the derivative of the natural log of 25 over n is just negative 1 over n. That's what's gonna go up here, negative 1 over n. And forgive the edge of the board, there's a closing bracket right there too. These n's cancel. So we really have e to the power of n times natural log of 25 over n. I'm gonna put that n back up. And then I'm gonna know that e and ln will cancel. Like they are equivalent to just not even being there and having this argument with the power of n the way that it moved. That's the new thing. Okay, so we're ready. 25 over n to the power of n. Now we're gonna multiply by this expression. What's really just 1 times this, so natural log, 25 over n, plus n times negative 1 over n, which is just subtracting 1. Because we have now found the derivative, Setting all of this equal to 0 will tell us where changes happen, where increases become decreases, where decreases become increases, or at least, if anything, the growth in the graph can be studied. And we want to know where the growth in the graph stops, because if we're looking at where the graph increases and then starts to decrease again, that value right there is the maximum. So we need to solve this equation. Now, step back, get some eraser in. We don't need this note down here about the derivative of natural log. I need to take this factor. We have a zero product property happening. I need to take this factor and set it equal to 0. Heads up, it's never going to equal 0. It'll in fact never be negative because we're always using positive values of n. So the inside will stay positive. And there's no number you can make this that it actually, as soon as you pick that number, you'll get a 0. So we don't even need to look at that factor being equal to 0. What we do need to do is look at this factor being equal to 0. So that's natural log of 25 over n subtracted by 1 equals 0, which really just means that has to equal 1. So anything to the power, like how do I say this right? So the natural log of 25 over n equals 1, then that means that there must be an exponent. So the technique that I want to use here is I want to take and raise both sides to the power of e. That's going to make this e and ln reduce. We know this is always going to be a positive. We're never going to be 0. So this is still within the domain restrictions that we need. And then e to the 1 is just e. So we have 25 over n equals e. Solve for n. A little bit of multiplication, cross multiply, whatever you will. We wind up with n equals 25 over e, which is approximately some number around 9.1. We don't have 9 divisions to make though. 9.1 divisions to make. How are you going to add 9.1 things together when every plus sign connects 1 and then a second and then a third whole integer values? So we're just going to floor it and we're going to say n equals 9. In other words, this question mark right here happens at 9. And if I plug this number into 25 over 9 to the power of 9, we'll get our max volume. Thanks for watching.